Yeah. Is there anything? Okay. Hello students, welcome to this interaction session. So we make use of this opportunity to ask questions, seek clarifications in the interest of an enhancing understanding of the subject. So there has been one question posed on the forum in the Google Sheet. First, I will try to answer that question. It's a very interesting question which will help learning all that we have taught. So as I mentioned in the introductory video, this is a beginner's guide to understanding random walk problems basically. How to understand, how to apply to various situations and contexts, and how do we explain the origin of macroscopic equations from microscopic processes within the framework of stochasticity. So that's what we have been trying to understand. Although we intended to cover many other techniques, the actual situation is that we are able to cover only a part of it in this part 1. Much of that we said we will do in Fokker-Planck equation, in master equation, theory of extinction. We are going to shift that to part 2 now. So this essentially is now going to be the covering theory for Brownian motion, this whole part 1 course. Now coming to the question that Mr. Vivek asked. So I'll first read out the question. When we first started with the generating function gf, they were defined as site summed, analogous to Laplace transform. You also said about the step summed gfs, which will be analogous to Fourier transform. Sir, will these step summed gfs also have important insights like moment generation, or useful by any means? Qualitative explanation will be helpful. So this is question number 1. I think the question I will slightly correct it. Please note that when we say site summed, first we have been doing site summed. Site or state, it can vary from minus infinity to plus infinity. It depends on the nomenclature. So if an infinite lattice, like a position, it can take up values, negative values from the starting position or positive values. So this is analogous to Fourier transform. So it is a site sum or summing over the states when they are discrete and countable. Then that becomes equivalent to Fourier transform in the continuum analogy, not Laplace transform. In contrast, step summing is analogous to Laplace transform because if you notice, steps are only positive quantities. They are defined only in the positive directions, just as Laplace transform is defined for a time variable in the positive direction. So that is the main difference and what we must note. Excuse me. So with this, I must say that more often we use a site summing, and most of the moment generation we have done are in respect of site summing. However, step sums are also useful when the domain does not permit closure in terms of say Fourier transform or site summing. Then step summing could be useful. But step summing is a little more complicated. The same random walk problem, if we do by step summing, it will be more winded, more difficult. The generating functions are more complex expressions, so that is why we didn't do that. But we did one example where we did step summing. That is when we were discussing the return period or the return probabilities. The Paulius theorem, if you remember, we summed over the steps of the quantity called Wn0, that is the probability of finding the particle at the origin at the nth step. There was only one site was defined. So we developed an expression for the site summed, sorry, I must correct, step summed generating function. So you may basically remember that the analogy is with the Laplace transform. So it is a tool for solving equations. So step sum or site sum are tools for solving discrete equations. For all moment generation purposes, it is the site summing which is useful, because its derivatives directly give you moments over states. Yeah. So that is one point I would emphasize. I hope it answers your question partly. Now the second question is, in Gaussian plume model, the reflection of plume is considered for virtual stack with the x plus h Gaussian term. Logically, it feels like if no reflection is considered, there is no need to consider the second term with x plus h. Even textbooks and articles on internet does not consider the reflection term, but as per random walk with the absorber, the absorption term should be there, that too with a minus sign. Kindly explain. Now, I think there is a bit of a mixing. Gaussian plume model is a very specific case, but you look at basically a diffusion problem. If you have a diffusion problem on an infinite lattice, then of course you have the free particle solution. Simple e to the power minus x square by 4 dt is the Green's function, or is the fundamental solution. If you have one barrier, and if the barrier is whether it is reflecting or absorbing, or even more complex case of mixed barriers, something has to be done with regard to the barrier. It cannot be a free solution. So at least for the case of purely reflecting and purely absorbing barriers, the concept of introducing a virtual source helps develop a solution. You can actually solve the problem, it's much more long-winded, without using any of these virtual sources. The history of using these virtual sources goes back to electrostatics. You must have heard of using an image. For example, solving a point charge in front of a conducting plane. So it's basically you have to solve the Laplace equation in front of the conducting plane, with a half space Laplace equation with a point charge. It's somewhat complicated. Whereas you can simply put a virtual charge and argue that moment I put an image charge of the opposite sign on the other side, it accounts for the presence of a conductor to the right hand side of the entire plane. So whatever potentials you will get in the presence of these two charges will be exact solutions of a point charge in front of a conducting plane. So this logic is used, adopted for a diffusion problem. It's a bit of a nice ingenuity, and it's exactly true for diffusion as well as for random walk. Random walk is a specific discretized case of diffusion. So if you have a reflector, basically means there will be a virtual source which will add to the existing contribution, because it will add paths. The paths which would have crossed over to the other side are reflected back. So the virtual source simply substitutes for those paths, and that is why a plus sign is introduced. If you have an absorber, those paths which would have somehow come back are all absorbed. So this is exactly equivalent to a negative sign charge, negative source. Same virtual source, but a killer source which kills paths. So there is nothing called a negative source or a negative walker, but it's a mathematical construct coming from electrostatics, as I mentioned, and it solves the problem of absorption at boundary correctly. You cannot get the correct solution if you do not have an image source of a negative sign in the presence of an absorber. So that is not correct to say that image sources are not mentioned. If somebody does not mention image source, then he must be actually solving the problem from first principles, from the very beginning, in the presence of a source. So you have to put a condition there, boundary condition, and solve it. That is for absorber, for example, you use the condition that the probability is 0 at the absorber, and then you have to solve. Then the normal Fourier transform method or the the site sum method doesn't work. It's a half space. Perhaps you should use a sine transform maybe for that. We have done it in one of the succeeding videos, where how sine transform solves the same problem. But if you have now two absorbers, a bounded space, as we do in Gambler's ruin problem, then the single image methods don't work. In fact, image methods become increasingly complex, virtual source methods, because these images cause images on the other plane. So the image of one absorber or reflector will have images, its images on the other absorber. So you have a series of images. People have constructed these solutions also, but then in those cases it is much better that you directly solve the equation, and that is how you get so-called eigenfunction expansions and all that. And it's a very specific thing for bounded problems. So one will have to, we have not done that in this exercise because I thought it's a bit of an advanced method of solving. There is a purpose and there is usefulness for image methods, and one should exercise caution. Have a happy learning. Yeah. Thank you. Any other questions? If anybody is there, you can chat. Yeah, I can add kind of a general philosophy of what we have been doing for enhancing your interest or curiosity. So basically we are learning how to gradually build models of increasing complexity, refinement, so as to take up wide variety of problems. So random walk is just the beginning. Then the kind of assumptions we make moment we talk of a stochastic process, how the stochastic process is different from a classical statistics. That concept is very important. There is an indexing, there are steps or equivalently time, so it has to be time ordered or step ordered processes, so not just random collection of data. So once we do that, even that is very complicated. The real world problems are far more complex, but very large class of them can be reduced to what are called as the Markov processes. So we come into Markov processes, and the uniqueness of stochastic subject is the existence of transition probability. It's a very unique concept, although in statistics somewhat like condition probability, the meaning, it assumes a different meaning moment a time ordering is introduced from now to the next. That is the concept of a transition probability. So then we form how to formulate equations. So equations which can be tested. So one can do simulations, of course, large number of simulations, and then how do you interpret the simulations? You need an analytical guidance for that, and that's what we have been attempting, to get an analytical guidance. The real problems may not be solvable analytically, but the results of the analytically solvable problems will be lifetime guidelines for you to interpret the numerical simulations. So in that context, how to go from paths to probabilities, how to develop equations for probabilities if it is a random walk, then the implication of Chapman-Kolmogorov equation for Markov processes, how to move from discrete to continuous. Then it takes us to the concept of differential equations. Then we see some connection with whatever an engineer learns in the form of a diffusion equation. So there is a connection, but there is an interpretationally different perspective in here. Then how to solve the presence of complex things like absorbers and reflectors. So that is the way this subject we advance. So from differential equations in the conventional space, we still haven't answered the question what creates this randomness in a physical system, in an engineering system, and then we go to Langevin equation, which gives you at least the first level of model where there is basically a velocity fluctuation coming from a thermal system, and that is the source of randomness, and how to model and how to go from there to probability density description, and that is how we end this subject. We can solve wide variety of problems, applications to transport phenomena, escape from barriers, for example, is a very interesting subject. Why do we get, how do we have processes like nucleation taking place, even though thermally the processes require large bit of energy, but still they happen, and the consequences of all this perhaps we will take up in the part 2. This is overall the perspective that I think I should share with you here. So good. The question on which programming language we will use for last week classes on numerical solutions. So I have given one example, I think in it will be L56 or something, and I'm going to do another one on a method of numerically solving. Look, my suggestion is this. I am familiar with Mathematica, so I write my programs in Mathematica. Today it is accessible in most institutes, I suppose, so it becomes easy. I am not very familiar with many other softwares, so that I suggest you learn yourself, but classical programming language is sufficient, that is Fortran and all that, and MATLAB of course has all the features of Mathematica or even more maybe, so MATLAB is definitely good, which I am not very familiar. So right now I will be teaching you in Mathematica, and it is up to you taking it to any other language. That much I can say. And the numerical simulations we will do are simple. How to sample, for example, in a Langevin dynamics, how do we do? So there is a little subtle aspect, that's why I thought I will actually demonstrate numerically, so which I have done. Then of course probably we will go back and see the validity of central limit theorem. We will do a nice simple simulation for one example at least, and that's what I want to do. And some actual random walk simulation, very elementary, but it's instructive. That much we will do, but all in Mathematica language. So we'll wait for a few more minutes if there are no other questions. Okay, one more question, Mr. Yadav, how to prepare for final exams? So there will be no question outside of what has been taught. And since this class specifically, in fact, we have focused on deriving 90% of them. There is no PPT based lectures if you have noticed, and we have taken trouble to derive every step. So the idea is to inspire you into analytical thinking and not just use the formula but to know how the formula comes. So it's much more difficult for me to ask a question to you because I cannot ask you, you derive this because everything is available. So most of the questions will be problem types. I suggest that if you go through the notes meaning the entire video and make your notes on each of these videos, almost all the problems will be from within that. There will be some questions, of course, will not be exactly the same wordings as we teach in the class. It will be about mapping a real world problem to the random walk problem, for example, and that is what the idea of learning is. So there will be a question of, as I gave in your in all the assignments, more or less the entire format of the assignment will be used in the final exams. Okay, so there will be question could be on a like as I mentioned in one of the examples of a drying of a lake problem, the various days, just to demonstrate that such models that we are building have wide-ranging applications, although they are a little ideal. So that I think you should be able to quickly grasp all that, and if there is a the need that there should be a hint, we will give that hint also. But main thing is how to use the formula after learning how to derive it. That's the whole idea of these exams, and it will be simple. In the, let me tell you that the final exam questions will be simpler than all the assignment questions that you have faced. One suggestion still I may give that as much as possible I have tried to keep notations distinct. Same notation does not have two meanings, but then it's a that way very wide ranging course. So some symbols have to be contextualized. So you must be careful when you read the notes. You must be careful. For example, when I say F. In some places it may be ultimate probability, in some places it is the probability of arriving at a point in K steps. So all that is there, you must contextualize and define. And notation in itself doesn't mean anything. Although W has been uniformly used for probability, occupancy probabilities, and that way I think we have tried to maintain that uniqueness, but it's not possible all the time. Yeah, so if there are no more questions, maybe we can wind it up. So if there is anyone waiting for a question, please come within a minute or so. So or else we're going to close this. Yeah, I think we will close this.